Hello, this is the fourth video of the Second Order Differential Equations 3 series on modelling with second order differential equations for OCR Pure Core Further Mathematics. And it looks at solving simultaneous differential equations. Many real-world situations are modelled by two or more differential equations involving more than one variable. Simultaneous linear first-order differential equations can be solved applying the methods for linear second-order differential equations when there is a system of differential equations. For example here, dx by dt equals x minus y, together with dy by dt equals minus x plus y. Note that here the dependent variables are x and y, and the independent variable is t. Predator-prey equations are usually a pair of first-order nonlinear differential equations, frequently used to describe the dynamics of biological systems in which two species interact, one as predator and the other as prey. A simple model of a predator-prey system assumes that predators increase at a rate proportional to the number of prey available, and that prey increase at a rate proportional to their number, but are killed at a rate proportional to the number of predators. This is depicted in the graph below. If we let the number of predators be x and the number of prey y, then dx by dt is proportional to y, or alpha y, for some alpha constant. And dy by dt can be written as beta y minus gamma x, noting that alpha, beta and gamma are all constants greater than 0. This then is an example of a system of differential equations. Continuing the example on the first slide, if we look at that second equation, dy by dt equals minus x plus y, we can rewrite that as x equals y minus dy by dt, and then differentiating dx by dt will be dy by dt minus d2y by dt squared. If we then substitute for dx by dt in the first equation, we can rewrite that as being the dy by dt minus d2y by dt squared equal to, and again substituting for the x as y minus dy by dt minus y. Rearranging this will give us d2y by dt squared minus 2 dy by dt equals 0. This is a second order linear differential equation which we may recognise the form of, having dealt with this in the previous video series. So we can apply the auxiliary equation. Let's use lambda, and we'd find that lambda squared minus 2 lambda equals 0. Factorising gives us lambda equals 0, or 2, and thus the general solution that y equals a, e to the 0 being 1, plus b e to the 2t, noticing that the independent variable in this case is t. If we then go on to see that dy by dt would be 2b e to the 2t, remembering that x equals y minus dy by dt from that system of equations will give us a plus b e to the 2t minus 2b e to the 2t, a minus b e to the 2t altogether. First, for general solutions for those two simultaneous differential equations at the top of the page are x equals a minus be to the 2t and y equals a plus be to the 2t. Having got that general solution, if we are given some other information about the values of x and y at some time t, either initial conditions or boundary conditions, we can find the values of the arbitrary constants a and b, and therefore the particular solutions. Here we're given initial conditions that x equals 1 and y equals 3 when t equals 0. So, at t equals 0, applying these conditions, we can say that 1 equals a minus b and 3 equals a plus b, using these two equations. When we solve those two simultaneous equations, this gives us a equals 2 and b equals 1. Therefore, the particular solution in this case will be x equals 2 minus e to the 2t and y equals 2 plus e to the 2t. In summary then, when we have a system of differential equations, for example dx by dt equals a1x plus b1y plus some function of t, and dy by dt equals a2x plus b2y plus a different function of t, then x and y are the dependent variables and t is the independent variable. A system of equations can be solved by differentiating one of the equations and substituting it into the other, as per the example we've worked through. The resulting equation can then be solved to give general solutions for x and for y, both as functions of t. And the particular solutions may be found by using additional information given, either initial or boundary conditions. In the next video, we will look at the graphs of these simultaneous differential equations, plotting and interpreting the solutions.